Okay, then welcome back to the week 7 of the problem solving session of the Introduction to Fluid Mechanics course. So, again, we'll wait for 2 more minutes to see whether other students join, and if not, then we can continue. Okay, so we'll wait for 2 minutes and then we can start. Okay, so I think we can start, and then let the other students can join whenever they like. So that's completely fine. So let's begin with this week's session. Okay, so this week's from this week I must say we will be now interested in the dynamics of the viscous flow. So till previous weeks we will primarily concerned in the basics or the basic structure of fluid mechanics, of how or we are mainly interested in the basic fundamentals of fluid mechanics and basic flow parameters such as pressure and velocity, and primarily we are concerned in flow statics. Then we looked upon the fluid motion part, and dealt with flow kinematics, where we dealt with flow visualization and the various techniques used to aid our flow visualization, such as streamlines, streak lines, path lines, and even timelines. Okay, and but as the word itself implied, kinematics meant that we are only interested in the motion of the fluid, but other than the forces that are acting behind or causing those motions. Because if you remember, last week we were discussing about, or in the previous weeks we were discussing about the driving factors of the flow, such as flow over a boundary layer or flow within a pipe. I mentioned that the driving factors in such kind of flows are, in the case of boundary layer flow, it is the inertia of the flow field, the inertia of the incoming flow, and in the case of the flow in a pipe, it is the pressure gradient that exists between the two ends of the pipe, right? So those are considered to be a driving force. So by driving force, I primarily meant that the forces that act upon the fluid that generates its motion, or that causes the fluid to flow. Okay, so from this week onwards, we will be primarily talking about the forces that exist in the flow forces that exist in the flow field, and that generate or induce flow in the concerned geometry or control volume that we are focusing upon. Okay, so for this week we will be primarily concerned on two very important equations, or two very important subtopics. That is, first of all it is the Euler's equation, and then the Bernoulli's equation, where Bernoulli's equation is a specialized case of the Euler's equation. Okay, so again, for the sake of saving time, since this week's topic is a bit heavy or a bit hectic, I will try to skim past the revision portion a bit faster than usual, and don't emphasize upon each and every steps, because that would become a bit repetitive. Like, I don't mind to be a bit repetitive, but since the topic for the content of this week's session is a bit more than the other 2 weeks, especially the previous 2 weeks, so I will try to skim past the topics of the revision portion a bit faster than usual. I will try to obviously I will go upon the equations, the steps as well, but I will not enunciate or elaborate each and every steps like the way I did in the previous 2 sessions. Okay, and moreover we also have some lengthy problems to solve, so in order to save time I will try to move past this revision part a bit faster than usual. Okay, I hope you understand, and moreover if you have any doubt you can just ask me or drop that doubt in the discussion forum, or just go back to the lectures by Professor Chakraborty. Okay then. So in this first step we try to, or in this first case we try to derive the governing equation for the fluid motion along the x direction. Okay, which is primarily the momentum equation, and say the force equation along the x direction for this particular fluid element is given by this. The summation of all forces along the x direction is max, delta m or just m, that's completely fine, m into ax, and where I used delta m so that I could denote the mass of a element, fluid element, rather than the entire control volume. Okay, control volume of the fluid that we're focusing upon. Okay, so just a few minutes, just a few seconds, just a minute. Okay, yeah. So here P is the pressure that acts upon this face of the fluid element, and P plus dou P by dou x into delta x is the pressure that acts upon this face of the fluid element. Okay, and the edge length of the fluid element is given by delta x along the x direction and delta y along the y direction. And let's consider that the depth of the fluid element within this paper sheet is say 1. Okay, a unity. Then the area upon which the pressure acts would be delta y, or delta y into 1, so we're ignoring the into 1 part, multiplication with 1 part, so we're just ignoring that. Again same goes for the area upon this area as well, right? If you were to measure the pressure, net force that act along the y direction, then the area would be delta x into 1. Okay, so that's the concept. Then for forces along the x direction, we just do the net force balance and write the governing equation here. So the net forces would be P delta y on this surface, then P plus dou P by dou x plus delta x into delta y on this surface, minus sign because of the direction of the force applied, and rho bx delta x delta y, that is the body force that acts along this fluid element along the positive x direction, that's why a positive sign. Then max denotes the net inertia force, so it is given by rho delta x into delta y into 1 to consider the depth along the z direction, that would comprise the volume of the fluid element. Then rho into v would give us the mass, right? And the acceleration is given by the Eulerian form of the acceleration, given by dou u by dou t plus u dou u by dou x plus v dou u by dou y plus w dou u by dou z. Okay, I hope this is clear. Oh, I'm sorry, it's just zoomed in too much, so I hope it's fine now. Yes, so this expression is clear, I guess. And once we simplify this expression, we get that minus dou p by dou x plus rho bx is equal to rho dou u by dou t plus u dou u by dou x plus v dou u by dou y plus w dou u by dou z, where this is a simplification of this part. Okay, it's just a simplification of that part, and we this rho delta x delta y is cancelled out on both the sides. Okay, then here rho bx denotes the net body forces that act on the fluid element, minus dou p by dou x, or the pressure gradient indicates the net pressure forces that act on the fluid element, and this acceleration term denotes the net inertia force, of the fluid element. Okay, and this is essentially the Euler's equation along the x direction. Similarly, along the y direction we would have dou p by dou y plus rho by is equal to u dou v by dou t plus u dou v by dou x plus v dou v by dou y plus w dou v by dou z. Similarly, along the z direction we would have minus dou p by dou z plus rho bz is equal to rho dou v by dou t, dou w by dou t plus u dou w by dou x plus v dou w by dou y plus w dou w by dou z. Okay, so that's just it's just the template of the component or the Euler's equation along the x direction. Similar form can be obtained for the y and z direction as well, but just by replacing the velocity component. Okay, and the derivative and the body force term. Okay. So now we discuss an example, and I'm just recalling the examples that was discussed by Professor Chakraborty, so that we have a proper revision and we could apply those concepts in the problems that we're going to solve for this week's this week's session. It will aid you to solve the problems in your current week's assignment. Right. So the velocity field is given by v is equal to ax I cap plus ay j cap, and g the gravitational acceleration acts along the negative x direction, okay, which essentially comprises the net body force. Then we are asked to find the pressure at point P1, Px1 y1 and Px2 y2. Okay, so now applying the Euler's equation of motion, because if not mentioned yet, so we can essentially consider the net viscous force or net we can consider the fluid to be inviscid, so the viscous components would not be there, because here also in the above fluid element, if I go back, we have not considered any viscous stresses that act along the surface of the fluid element, right? We have ignored that. So essentially we are discussing, or we are in the inviscid regime, right? We are considering an inviscid flow. So essentially this example also discusses an inviscid flow where the velocity component is given by this expression. Okay, so applying the Euler's equation of motion, we get that again I will not enunciate each and every term, but let us just go into it. Then that minus dou p by dou x plus 0, because body force is 0, is rho a square x. Similarly, minus dou p by dou y is equal to rho a square y, and minus dou p by dou z minus rho g is equal to 0. Okay, so these expressions would give p is equal to minus rho a square x square by 2 plus some function of y and z and a constant. Similarly, this equation will give p is equal to minus rho a square y square by 2 plus some function of x and z and plus some other constant. Okay, because we are dealing with partial derivative, so integration with respect to y would mean a function could exist which would be a function of x and z that would be 0 if we take a partial derivative with respect to y. Okay, similarly this equation would reduce to p is equal to minus rho g z plus some function of x and y plus some constant c3. Okay, then we have that f1, if we compare these three expressions, we will get that f1 is equal to minus rho a square y square by 2 minus rho g z plus c1, f2 is equal to minus rho a square x square by 2 minus rho g z plus c2, and f3 is equal to minus rho a x square by 2 minus rho a square y square by 2 plus some constant c3. Then thus we have pressure is equal to minus rho a square x square by 2 minus rho a square y square by 2 minus rho g z plus some constant c. Okay, when c can be, you can manipulate it in any way possible, it's just a numerical constant. Okay, then since we know that v is equal to a x I cap, let me write it properly, v is equal to a x I cap minus a y j cap, then the magnitude of v would be basically the square root of a square x square plus a square y square, right? So simplifying this expression, we get that p is equal to minus rho v square minus rho gz plus c. Okay, where v is equal to u square plus v square, u is equal to ax and v equal to minus ay, as we just discussed here. Then if we take these terms to the left hand side, we will get p plus half rho v square plus rho gz is equal to some constant c, which is essentially the Bernoulli's equation that we are considering. Okay, and you will see how this kind of flow has resulted or given us a very have reduced the Euler's equation motion to Bernoulli's equation. Why? Because as discussed by now we will discuss actually, and I guess this example was also discussed by Professor Chakraborty in the previous session as well, that this kind of flow essentially denotes a stagnation point flow. So we will see why. Okay, so the rate of deformation for this flow is given by dou u by dou x plus dou u by y plus dou v by dou x, which again essentially is 0. Which essentially is 0, because u is equal to ax and v is equal to minus ay, then dou v by dou y is 0 and dou v by dou x is equal to 0. Similarly, the angular velocity omega xy, which is equal to half dou v by dou y minus dou v by dou x, is again 0, because dou v by dou y and dou v by dou x are itself 0, like they individually are 0. That's why the flow is there are no considerable viscous effects because the rate of deformation is 0, and moreover the flow is irrotational because the angular velocity omega xy is also 0. And thus such kind of flows which are inviscous as well as irrotational denote a stagnation type flow. Okay, so as mentioned here, that such kind of flows and for such kind of flows, since the flow is irrotational, Bernoulli's equation can be applied between any 2 points in the flow field, which we will eventually see is one of the very important or very crucial assumptions made while considering Bernoulli's equation to solve a fluid flow problem. Okay, and we'll look into it why this is so crucial. Okay, because this equation in itself, let me go back. This equation in itself seems very elegant, right? It's very simple. It just shows that sum of some parameters or some function of some parameters are a constant, and thus it seems very elegant. But again, we need to make sure that what are those prerequisites or required parameters or required conditions that help us to assume this form of the equation to solve any kind of fluid flow problem. Okay, so that's very crucial, and we will discuss that eventually, and that is the actually the gist of today's session, that is deriving the Bernoulli's equation from the Euler's equation, considering several special cases, and then finally understanding how the popular form of the Bernoulli's equation comes into picture, and what are the assumptions that follow for this form of the equation to be valid for any kind of fluid flow. Okay, then we consider the Euler's equation of motion along a streamline and consider the flow to be steady. So the equation would then reduce to this form. Okay, how it is reduces, I'm not going to derive, because as I said, I will try to skip past the revision part. So if you have any doubt regarding the derivation, you can go back to the lectures, so that would be much better. But let us just go to the each and every steps and understand how the Bernoulli's equation is derived from the Euler's equation of motion. Okay, and what are different forms of Bernoulli's equation that may be applicable to different kind of problems that we need to understand before solving or approaching any problem. Okay, then in this equation, if we consider density to be constant, that rho is equal to constant, then this equation will reduce to this form. Okay, that P2 minus P1 by rho plus half V2 square minus V1 square plus GZ2 by minus Z1 is equal to 0. And if we rearrange these terms, we essentially get the Bernoulli's equation. Okay, the popular, the famous, elegant form of the Bernoulli's equation. Okay, and what are the assumptions that, let me just give a red box so that people can recall that this is an important equation. So okay, I hope that's fine, and let me even write it here. So and this can be erased, I guess. So okay, so if we look, this is the form that we usually encounter while discussing fluid mechanics, that Bernoulli's equation is given by P1 by rho plus V1 square by 2 plus GZ1 is equal to P2 by rho plus V2 square by 2 plus GZ2. And we tell that this is the equation that is used to find the pressure between any 2 points or velocity between any 2 points, or we just blindly use it while in our lab experiments when finding the dynamic pressure in a, or the, while finding the flow rate using the venturimeter. So these things become quite this equation can be considered to be taken in a quite granted, are considered to be quite granted. Like we just take these equations to be for granted, and assume that these equations are, you can apply it in any kind of flows and find the flow parameters. But actually this is not the case. They are very crucial assumptions that come into picture that follow these equations that are important to be satisfied before applying or before implementing Bernoulli's equation to solve any kind of fluid flow problem. Okay, I am emphasizing it again and again because this is the place, or these are the scenarios, or these are the situations where students make the mistakes, that they don't look upon the conditions that are required for the application of Bernoulli's equation and then just blindly apply the Bernoulli's equation and then get wrong answers and then fail to understand the basic fundamental concepts that are behind the derivation of Bernoulli's equation. Okay, so the assumptions are that for this equation to be valid or this equation to be useful, the flow must be inviscid. Okay, the flow must be inviscid. Secondly, for this form of equation, for this specific form of equation, the flow has to be steady. It does not mean that the Bernoulli's equation cannot be applied for unsteady flows. It can be applied for unsteady flows, and it has a certain form for it, which we'll eventually discuss. But for this form of the equation, the flow has to be steady. Okay. Then one more assumption is that the density has to remain constant, which is again a special case for incompressible flow. So if it is given that the flow is incompressible, we blindly cannot say that the Bernoulli's equation is applicable. We need to check whether the density is constant as well, right? Then only we can apply the Bernoulli's equation. Okay, and finally, this equation is only valid for any 2 points along the same streamline. Okay, it's very important. Like in many competitive exams and university level exams, this problem related to this condition comes a lot. Like they will give the flow will satisfy all the conditions, but once they ask, thus they will give 2 points in the question, and they will say that whether you can apply Bernoulli's equation to find the pressure or other flow parameters in these 2 points, and the flow may be inviscid, the flow may be steady, and even the density may be constant. But if the 2 points that we are concerned about, where we want to find the flow parameters, are not along the same streamline, then again this equation is not valid. Okay. So these are the very important, crucial conditions that we need to check before applying the Bernoulli's equation. But again, the special case is that if the flow is irrotational as well, because till now in these assumptions we have not considered about irrotationality. Okay, so if along with being inviscid, if the flow is irrotational as well, then we can apply Bernoulli's equation between any 2 points in the flow field. Okay, I would like to repeat it because it's very important. I'm saying that along with these assumptions, if the flow is irrotational as well, then we can apply Bernoulli's equation, that this form of the equation, between any 2 points in the flow field. Okay, so this is very important, and I guess we will even discuss similar problems in this week's session, but still I hope you remember it. Okay, then there are various forms or by which the Bernoulli's equation can be written, and this is one of the forms, that is the head form, where all the terms are in the unit of length or meter. So where P1 by rho denotes the flow energy per unit length, V1 square by 2g denotes the kinetic energy per unit weight. P1 by rho denotes the flow energy per unit weight. Okay, V1 square by 2g denotes the kinetic energy per unit weight, and Z1 denotes the potential energy per unit weight. Okay, where the flow energy per unit weight basically denotes the work done per unit weight to maintain the flow in the presence of pressure. Okay, and about this thing, about how this term comes into picture and what is its significance, Professor Chakraborty has taken ample amount of time to do the detailed derivation with appropriate diagrams to show the significance of this term. Okay, so I insist that you go back to the lectures to at least revisit this part of the lecture where he is discussing about the flow energy part, because sometimes people also consider it to be the pressure force, right? But a more correct way to describe it would be the flow energy per unit weight. Okay, so about this and the subsequent derivations, Professor Chakraborty has done a very detailed and very beautiful derivation regarding this. So I insist that you go back and revisit the lectures so that you can get the proper gist of the topic or the concept that we are discussing here. Okay, so that will be very good. So okay, so by definition, Bernoulli's equation states that the flow energy, the kinetic energy, and the potential energy per unit weight remains conserved as it is transmitted from one point to the another in a flow field. Okay, in which case a streamline. Okay, so there's the definition. Then we consider the Euler's equation motion with two assumptions. That is, first the flow is in viscid and the flow is along a streamline, and here we have relaxed the parameter of the flow being steady. Okay, so we are not considering the flow to be steady anymore. Okay, so then this is the form of Euler's equation. This is the form of Euler's equation that we get. Then simplifying this, we reach this form, and here if we consider rho to be constant, this is the form of Euler's equation that we get. Okay, and considering rho to be constant, so once we do the integration, we get that P1 minus P2 by rho plus half V2 square minus V1 square plus d Z2 minus Z1 is equal to minus the integration of 1 to 2 dV dou V by dou t plus ds. Okay, just 1 minute. I am having a bit throat issue, so I will just resolve that. Meanwhile, you can look into the equations and contemplate how these equations have been derived. So just look into it. Okay. Just a minute. Okay. Okay. So I'm sorry for the delay. I was having a bit throat issue, so the voice was becoming very cracky. So I hope you understand. Okay. Then once we rearrange this equation, we get that P1 by rho plus V1 square by 2g. Sorry, P1 by rho plus V1 square by 2 plus GZ1 is equal to P2 by rho plus V2 square by 2 plus GZ2 plus, we just take this integration in this side. So plus integration from 1 to 2 or 0.1 to 2 dou E by dou t into ds. Okay, and this is actually the unsteady form of Bernoulli's equation. So if the flow is given to be unsteady and all the other conditions, that is being in viscid, constant density and along a streamline are satisfied, then this form of the equation can be applied, which is popularly known as the unsteady Bernoulli's equation. Okay, and we in fact have one question regarding this form of the Bernoulli's equation. So I hope you are able to recall it. You may take a note of this equation, so that when we are going to apply or when we are going to consider that equation, that problem, then you can just try to put in the given parameters to the equation and then derive the solution. Okay. So just a brief overview that because this topic was discussed in depth by Professor Chakraborty. So for the sake of saving time, I will just give a brief overview or just read through it. So if you have any doubt, you can ask me. Okay. That is, Professor Chakraborty discusses the factors that make an originally irrotational flow rotational. Like if the flow is initially rotational, what are the factors that can turn the flow from irrotational to rotational? Okay, So Professor Chakraborty mentions that these are the following factors that may cause the irrotational flow to turn into rotational one. Okay, so that is, first is the presence of a solid boundary or viscous effects. Okay, then presence of shock waves. Okay, then thermal stratification and Coriolis forces. Okay, and these things I won't revisit again. You can just go to the lectures. Professor Chakraborty has discussed very has described each and every of these factors in a very described manner. So I hope that would be the better source for you to take notes or understand the concepts behind how the vorticity is generated because of the presence of walls or shock waves or thermal stratification or Coriolis forces. Okay, and but there's a very important conclusion that I wanted to arrive while discussing these factors, that this is a very important statement. Okay, again, this is it's a one-liner question that may come in GATE or ESC. So if one knows the concept, one can easily score the marks. Okay, but again, something that can be remembered. Okay, and if it is clear, it will remain in your head for a lifetime, okay, in your brain for a lifetime. So the thing is, again, just focus here, that if the flow is inviscid and irrotational, then it will remain irrotational even if there is a solid boundary present. Okay, why? Because since the presence of the solid boundary wall will not be felt because of the absence of viscous effects. Okay, so if the flow is inviscid and irrotational, then the flow will remain irrotational forever, no matter if it is confined in a wall or a boundary. Okay, so in essence, this kind of flows or this kind of condition is never possible, because there is no flow that is completely inviscid, or no fluid that has zero viscosity, or it is very hard to generate flows that are irrotational from the very beginning, because flows in its very nature are most of the times attached to a solid surface, which in turn generates the vorticity or makes the flow rotational, or even if needed, at least in the boundary layer region, which we'll discuss what is boundary layer and what are its properties. So we will discuss in the later part of the course, but just for the concept sake of learning the concept, that this is the case. Like, this kind of flows are very hard to attain in real life, but there are certain scenarios or certain conditions where we can generate an approximate condition of the current statement. Okay, see, this kind of flows or this kind of scenario may arise in the case of channel flows or rivers or very wide rivers. Okay, just consider wide and deep rivers. So in that case, the region in between the two ends or two edges of the river or two banks of the river, that is basically, if this is the river, a very wide river, say, so this region, essentially this region, the surface just below the fluid, just below the upper surface and considerably above the river bed, that region of the flow would essentially show this kind of nature. Why? Because since it is far away from all the boundaries, right, which actually has which are actually the generators of vorticity, so the viscous effects that turn the flow from irrotational to rotational, that will not be felt in this middle region. Okay, let me just draw it, so that would be better. So if these are the two edges or two banks of the river, then this is the region that I am talking about. So these regions, because of the presence of the edge of the river bank, it will be rotational. Okay, kindly ignore the direction of rotation of the eddies. So I'm just, and obviously drawing as well, so that's just for concept. So these regions will remain rotational because it is the vorticity is generated from the edge of the river. Okay, so this will generate the vorticity. Similarly, the river bed would generate vorticities again because of the boundary layer effect, so it will generate vorticity. But the fluid within, much above the river bed and just below the upper surface of the river. Why? Because the upper surface itself is again connected with the air. It is in contact with air, so which itself may cause some gradient in the velocity at the interface, which essentially will not generate vorticity, but may induce some kind of flows that may create vorticity. But just for being safe, I'm considering the leave the upper surface, just go below the upper surface and above the river bed. So that region can essentially be considered to be inviscid, right? And it would remain inviscid because okay, not zero viscosity, inviscid, because it is far away from all the edges and all the vorticity generators. So that is the concept that we are trying to say here. But again, this is just for approximation's sake, it is correct, but in reality it's not possible because there are various factors that come into picture while considering this case, like the very approximation of these regions being far away from the edges is very vague, because on the scale of the river, the effects of the edges is always felt, and also the effects of the river bed is also felt by the fluid, right? So on the scale of a river, okay, I'm not saying that in the small scale, on the scale of a river, the effect of river bed and the edges will always be felt, so it's very hard to generate a completely inviscid region, okay. And moreover, there are various organisms living in the river, for example tortoise and other creatures that again may generate, that again may be the that can again be the sources of vorticity generators in the rivers, okay. So it's again very hard to attain, but just if you're trying to conceptualize or visualize such kind of conditions, so I just wanted to give this approximation, okay. Okay then. So this is what is being discussed here. So okay, so this is just the explanation of what I was trying to give. So for example, if you consider 2D flow, it's just the explanation or the mathematical description of the above statement. So if you consider 2D flow, for the flow to be rotational, we need the angular velocity to be 0. So dou v by dou x minus dou v by dou y is equal to 0 for 2D case, okay. Again, for inviscid fluid or inviscid flow, let me consider it to be flow, okay, instead of fluid, let us say flow. Mu dou v by dou x plus dou v by dou y is equal to 0, okay. And here again, so you can see that since dou v by dou y plus dou v by dou x is equal to 0, I'm sorry, so okay, and dou v by dou x minus dou v by dou y is equal to 0, it is only possible when both these terms are identically 0, are individually identically 0, okay. So there are no velocity gradients present in the flow field, and thus there is negligible dissipation in the system, okay. And it is mentioned here again that viscous effects create dissipation in the flow field, and thus making the flow no longer a conservative field, basically no longer a rotational flow, okay. Basically, if the flow is irrotational, it is considered to be a conservative field, okay. So it is again one concept to be learned, so that's the thing. Since there is no velocity gradients, the dissipation term is essentially negligible in the case of such kind of flows, okay. So this is what I wanted to that is what these derivations try to imply regarding the statement that we just discussed, okay. That is, if the flow is inviscid and irrotational, then it will remain irrotational even if there is a solid boundary present, okay. So I hope this was clear. Then I will skip this. Okay, let us not skip that. Okay, so okay then, so we can take this example, but again we need to. Okay, I'll go through this example a bit faster than usual, because I have a lot to cover, and we have a very detailed problem solving session today. So okay, let's try to cover this example as fast as possible. Okay, so it is given that there is a plate given by this rectangle, and it is given that this plate is placed in such a way that is placed is placed here, and there is a flow that is being generated, that is being passed through these pores that are there in the lower edge of the lower plate, say, and where the velocity profile of this flow is given by v naught. Okay, and then the width of the plate is given by b. So if we consider this to be the center line, then the width of the plate about the center line is b by 2 and b by 2. Okay, and this plate is kept at the length of h. Okay, so here it is mentioned that the flow that comes through these pores are able to balance the weight of this plate. Okay, that there is a flow here. Let me just draw it. Basically the plate is levitating in this case, so the plate is placed here. So there is a incoming flow from the bottom edge of the bottom edge. So this flow is able to support the weight of the plate. Okay, so we are asked to find the weight of the plate, and the given assumptions are that the flow is inviscid and steady. Okay, so first of all we need to find a velocity field. Okay, say we want to find the velocity field along the x direction. Okay, so we need to find the velocity field in the x direction, so we need to know u of x. Okay, so from mass conservation, now first of all we consider a control volume which is given here. So we consider that this is the region where we will focus, we will have our entire focus and solve the flow within this region, only within this region. Okay, which is termed as our control volume. More about the control volume we will discuss while we are discussing the Reynolds transport theorem and the Navier-Stokes equation. That there we will see detailed analysis of what are the good choices for choosing a control volume, but for time being you can just understand it as a region that we are focusing upon. It is basically the Eulerian approach where we mention the control volume, so, or the region of our focus or our region of our attention, and this is the region where we are trying to solve the fluid flow equations. Okay, so if this blue dotted line represents the control volume, now we need to find the velocity along the x direction. Okay, because of this incoming flow, so the flow that is generated here may go up and get deflected, right? So this deflection will again create a velocity along the x direction as well, so we need to find that velocity field. Okay, so in this control volume, say the width of this control volume is x from the center line. Okay, so from mass conservation we would have v naught x into L, where L is the, let me just mark it so that it's not confusing. So L is the depth of the plate. Okay, so v naught into x into L is equal to, so area would be x into L, right? So v naught into x into L, v naught is constant, is equal to u of x h into L, right? So this area would be again be h into L, right? And here the velocity is ux, say it is ux. Okay, and again we consider that since the flow is inviscid, the velocity does not vary with y. Okay, then we get that u of x is equal to, just from this mass conservation we get that u of x is equal to v naught x by h. Okay, so to get the weight of the plate, we do a force balance on the plate and construct its free body diagram. Okay, let me zoom out a bit more. Okay, So now, since we know the velocity field along the x direction, okay, therefore using Euler's equation we can find the pressure by solving the Euler's equation along the x direction, right? So rho p by dou x is equal to minus rho ax, okay. Then ax would be equal to u dou v by dou x plus u dou v by dou y, but v, since v is constant, so dou v by dou y term will be equal to 0. So we are only having the x velocity term where the u or the x velocity component varies with x, okay, it's a function of x, so that will remain. So ax would be u dou v by dou x. So u is again v naught h by x into v naught by h, because dou v by dou x would be v naught by h. So ax would be equal to v naught square by h square into x, okay. So dou p by dou x would be given by minus rho v naught square by h square into x. So once we integrate, we get that p is equal to minus rho v naught square x square by 2h square plus some constant c1, okay. So if we assume that to find this constant, if we assume that at x equal to p by 2, p is equal to pa or atmospheric pressure, then we can find c1, okay. See, I am not solving the equation here, okay. I want you to solve that. So from the free body diagram, if you go back to the free body diagram, say this. So we consider that p is greater than pa, so that there is a net upthrust in the upward direction that is able to balance the weight of the plate, okay. That's why at equilibrium we will have p is equal to w plus pa, right. The net upward force is equal to sum of net downward force, okay, at equilibrium. Then w would be equal to p minus pa, okay. Thus to find the net upthrust or this weight, we need to integrate along from 0 to b by 2 and integrate this difference p minus pa along the area, along this area, okay. Let me go back, along this area. So since L is constant and since u is varying along the x direction, so we do the integration from 0 to b by 2 and just multiply it by 2 because the flow is symmetric along the other direction as well, okay. So this is what we have done. So the integration, since p is a function of x, so we need to do the integration along the x direction from 0 to b by 2, multiply it by 2 to cover the entire plate and just multiply with L to consider depth. So from that we will get that integration of from 0 to b by 2, 2 into p minus pa into dx dot into L is equal to the weight of the plate, okay. So again there is a discussion about the streamlined coordinate system or the Euler's equation in the streamlined coordinate system. So that I will not derive, I will just look into the final form of the equation. So along the streamlined coordinate, the Euler's equation of motion is given by minus dou p by dou s minus rho g delta dou z by dou s is equal to rho dou v by dou t plus v dou v by dou s, okay. Similarly, where s denotes the streamlined coordinate, okay, and or denotes the coordinate along the streamline, okay. And again, or for the direction normal to this in the direction normal to this streamline, the governing equation or the Euler's equation is given by minus dou p by dou n minus rho g dou z by dou n is equal to rho an, where an or the acceleration along the normal direction is given by minus v square by r, or the, which is basically the centripetal acceleration, okay. Then this equation essentially tells us that if there is a curved streamline, there is a pressure gradient along the streamline, okay. So if the streamlines are curved, okay, so this equation essentially tells us that there is a net pressure gradient along this streamline, okay. So you may consider why we want to consider this term. Like if we consider it to be a piezometric pressure, like you consider it to be p star, okay, sorry, consider p star is equal to p plus rho gz, okay. Then just consider that then if we take the derivative along the normal direction, so we will get this expression, right. So that pressure or the piezometric pressure varies if there is a curvature along the streamline, okay, which is given by this equation, okay. Again, if the streamlines are parallel to each other, the radius of the curvature r tends to infinity. Thus there is no pressure gradient in the across the streamwise direction between 1 and 2 because the curvature of streamline is infinity, okay. So I'm mentioning this because these are these are conceptual questions, like what is the pressure gradient in the case of curved streamlines. Okay, so that you need to know, like if the and that you need to, that you will know for sure if you remember this equation, right? That since there is a finite curvature, that there is some certain value of r, there will always be a finite value of the pressure gradient. If r is increasing or r tends to infinity, this term will go to 0, so the pressure gradient will itself be 0, right? So that is what I wanted to see and wanted to mention. Moreover, this kind of questions may again come, these conceptual types of questions may again come in competitive exam, so it's better to remember the concepts. Okay, so okay, so after that let's directly now dive into the problems. So again, as I mentioned, this week's problems are a bit more extensive compared to the last 2 weeks or the kinematics part. So let us directly go to the questions. Okay, so the first question, let me go back. Okay, the first question is given here, given by here. Let me just zoom it a bit. Okay, so this is the first question, that an incompressible frictionless flow field is given by this. Okay, this is the velocity field given where a is equal to 2 second inverse and b is equal to 2 second inverse, and x and y are in meters. The fluid is water. Again, very important to know the density, and the body force or the acceleration due to gravity is along the j direction, positive j direction. Okay, determine the x component of pressure at the point 2, 2. Okay, so again, since the flow is frictionless, you can directly now consider the Euler's equation of motion. Moreover, now which coordinate direction to consider? Since the body force is along the y direction, so we can consider to simplify our calculations, we can consider the x component of the Euler's equation, because there is no body force there, then we can directly solve it. So there will only be one term to consider, the force due to the inertia term we need to consider, and the body force term, since it is 0, so that term will not be there. So the equation will be much more simpler compared to the Euler's equation of motion along the y direction. So that's the algorithm for solving this equation. So if we try to solve it, I have solved it. So here v is ax plus by ik plus bx minus ay jk. So if the flow is steady and since the if the flow is steady and the body force is 0 in the x direction, the Euler's equation of motion along the x direction is given by this equation, right? Once we substitute the value of u and v in this equation, we will get that dou p by dou x is equal to rho ax plus by into a plus b into bx minus ay. If we simplify it further, we get that dou p by dou x is equal to minus rho a square plus b square into x. Okay, and we need to find a pressure gradient, right? We are asked to find a pressure gradient at the point 2, 2. So just substitute the value of a, b, rho and x in this expression to get that dou p by dou x is equal to minus 16,000 Newton per meter cube. Okay, this is a unit because pressure is Newton per meter squared, then again divided by one more length scale, then it is meter. Okay, so it is Newton per meter cube. So the next question is which of the following is not correct? Okay, not correct. So the first is the Bernoulli's equation can be applied to find the pressure difference between any 2 points in a steady rotational flow, even if the points do not lie on the same streamline. Okay, so this statement is correct, because if the flow is irrotational, then I told that the final condition, that is the flow along the streamline, can be relaxed. So the Bernoulli's equation can be used to find the pressure between any 2 points in the flow field. So this equation is correct. Okay, so let us look into the second equation. Let's look into the second statement. Okay, Bernoulli's equation cannot be applied to find pressure difference between 2 points if the flow is rotational. Okay, so again this statement is not correct because it is not mentioned that the 2 points are on a streamline or not. So if we consider the 2 points to be on streamline, then even if the flow is rotational, the Bernoulli's equation can be applied to find the pressure between those 2 points. Okay, so this statement is wrong, because if the 2 points are along the streamline, then Bernoulli's equation can be used to find the pressure difference between the 2 points. Okay, so this statement is wrong. Then statement C says Bernoulli's equation is valid if the cross product of velocity vector and the vorticity vector is perpendicular to the line joining the 2 points and the flow is steady. Again, so this statement is correct, because there was one expression or condition where V cross omega dot dl. So if this term is 0, then again the Bernoulli's equation simplifies to the classical form that we discussed. So if that's the case, then Bernoulli's equation is valid for finding the pressure between any 2 points in the flow field, right? So again, this is correct. Okay, and finally, the Bernoulli's equation is not valid for an unsteady flow. Okay, again, so from Bernoulli's equation, I guess from here we mean the classical form, that is P1 by rho plus V1 square by 2 plus GZ1 is equal to P2 by rho plus V2 square by 2 plus GZ2. So this is the Bernoulli's equation, and the special form is known as the unsteady Bernoulli's equation. So Bernoulli's equation that we are discussing, the classical form, again is not valid for an unsteady flow. That's why this statement is correct. So the only incorrect statement here is option B. So our required answer is option B. Okay, that is Bernoulli's equation cannot be applied to find a pressure difference between 2 points in the flow field if it is rotational. Okay, done. So question 3 is water flows steadily. Let me underline the key terms. Water flows steadily through a vertical 2.5 diameter pipe, 2.5 centimeter diameter pipe, and out the 1 centimeter diameter nozzle to the atmosphere. So P2 is equal to PA. Determine the minimum gauge pressure required at section 1 to produce velocity at the nozzle exit of 9 meter per second. So V2 is 9 meter per second. So we need to find the pressure at point 1 that would generate a velocity of 9 meter per second at the exit. Okay, so here, since it is mentioned that the flow is steady, so here we can directly apply the Bernoulli's equation considering a streamline from point 1 to point 2. Okay, we can consider a streamline from point 1 to point 2 and then apply that Bernoulli's equation to find the pressure at point 1. Okay, and obviously mention the required statements as well. Okay, so if we go back there, we can see that, yeah, so this is a diagram. So if we consider the following assumptions, that is the flow is steady, constant density, and inviscid, and the 2 points 1 and 2 lie along the same streamline, so then we can apply the Bernoulli's equation given by this expression, right, the popular form of the Bernoulli's equation. Then here we do not know P1 and V1. Okay, so these two terms are unknown. Z2 minus Z1 is known. Z2 minus Z1 is equal to 3 meter. Okay, if I zoom out a bit more, so from this we can get that Z2 minus Z1 is equal to 3 meter. Okay, so now since V1 is unknown, we use continuity equation to express V1 in terms of V2 because V2 is known, and then simplify the equation further because then only P1 will be unknown. Okay, so we need to substitute V1 in terms of V2 using the continuity equation. Okay, so from continuity equation we get that A1 V1 is equal to A2 V2. Let me zoom it a bit more. Okay. So from the continuity equation, we get that A1 V1 is equal to A2 V2. Then V1 is equal to A2 by A1 into V2. Okay. Then if we substitute it in this equation, then we get that P1 minus PA, because P2 is equal to PA as given in the question, is equal to rho by 2 V2 square minus A2 by A1 V2 whole square, because V1 is A2 by A1 into V2 from this expression, plus plus rho G Z2 minus Z1. Okay. Then just substitute the value of density, the diameters, to find the area and the velocity given. So if we do that, rho is 1000, so substitute it by 1000. Then if we take V2 out from this expression, which is equal to 9 meter per second, then A2 by A1 is would basically be the ratio of the square of the diameters, right? So and again rho into G, so it will be 1000 into 9.81 into 3, because Z2 minus Z1 is 3. So once you do this calculation, we get that P1 minus PA is equal to 68893.2 Pascal. So if we look back into the question, we get that since we are asked to find a gauge pressure, we essentially need to find P1 minus PA, right? That would essentially give us the gauge pressure. So P1 minus PA would give us 68893.2 Pascal. So our correct answer would be option number B. Okay. So for our next question, we have, what is the pressure gradient normal to the streamlines for a steady flow in a region where streamlines are straight in a horizontal plane? So we just now discussed that if the streamlines are horizontal to each other, or are straight lines in a horizontal plane, then the pressure gradient along the streamlines is 0, right? So the correct answer would be A. It's quite simple. So, but again, we need to remember the concept. So it's 0. Okay. Let us look into the next question. Okay. So this is a problem that is similar to what we discussed, similar to the problem that we just discussed. So it was a flow through the porous media, so or a porous surface, because there was a flow through the wall. So extremely sorry for the interruption. So okay, so in the previous example we saw that there was a flow through this bottom surface, right, which was given, whose velocity profile was given by V0. Okay, again it's just an approximation for the given scenario, because it in general that will be very complicated to represent velocity through those porous media by a constant value. But just for our sake of analytical simplicity, we assume that the velocity profile is actually V0 through this porous surface. Okay, but in this example we have that let us go to the example. The surface itself shows that the lower surface is a solid surface, so there is no flow through the solid surface. Okay, through the solid surface. So let us go to the question. So the question is, two circular plates are separated by a liquid layer as shown as in the figure below. Okay, the lower plate is stationary, so this is stationary, and the upper plate moves downward at a constant velocity v. Okay, so this is interesting. It is mentioning that now in the previous example we had that the plate was held stationary because of the flow impinging upon the plate in the upwards direction. Okay, but in this case now the lower plate is steady. There is a fluid that is being that is in between or sandwiched between these two plates, and this upper plate is moving downward with a velocity v. Okay, so essentially this the motion of this upper plate would induce a flow in the outwards direction, Okay, basically it will squeeze the fluid out of this region and then try to reduce this height b as it moves down. Okay, so I hope you understand the scenario or the scenario of the problem that we are discussing. Okay, then the radius of the top plate is r, and the liquid is squeezed up in the transverse direction between the plates, just what I mentioned, and the flow is in viscid. Okay, so the question is, what is the speed at which the liquid comes out of the gap between the plates in the radial direction? Okay, so we need to find the velocity vr, the radial component of velocity in this direction. Okay, so again we apply the similar concept. We choose a control volume within this region, which is not exactly at the outer surface. So let us choose a control volume at a distance r from the center line. So it will be the control volume, and this distance will be some small r. Okay, so again we need to apply mass conservation to find the velocity component along the radial direction. So let us go back to my solution that I obtained. So from mass conservation we have that pi r square into v. So why pi r square into v? Because the plate is moving in this direction with velocity v, and the area of the plate that is pi r square, and the net fluid that this motion displaces will be given by pi r square into v, right? And the net fluid that comes out would be from the periphery or from the lateral surface area of this fluid, or if you consider this fluid to be of cylindrical shape, then the surface area through which the fluid comes out is actually the lateral surface area of a cylinder, right? So which would be given by 2 pi rh. Okay, so 2 pi and r with the radius of this control volume, and the height is b, the instantaneous height is b, right, multiplied by vr, which is the radial velocity along this direction. Okay, so if you simplify this, pi and pi will get cancelled, r would be this square term would get cancelled. So vr would be v into r by 2b. Okay, where it is not actually v into r, but this term is not v into r, but it is v or the radial component of velocity, so v subscript r. Okay, so now we are asked to find so that is the expression of the velocity. So if we go back to the question, we would have the correct answer to be C. Okay, C. Now let us go to question back. So what is the variation of velocity with time? So we need to find dou vr by dou t. Okay, again it's very simple, just take the derivative of the velocity field along the radial direction, because we already found vr. So dou vr by dou t would be equal to minus vr 2b square dv by dt. Why? Because the radius of the control volume that we have chosen remains constant. So the only parameter that varies in this expression, that is vr is equal to v into r 2b square. So only expression that is time dependent is b. Sorry, it's b square, it's 2b, right? So the only expression that is time dependent is b. So vr by 2 essentially remains constant for the chosen control volume. So we need to take the derivative of b inverse. So it will basically be minus b minus to the power minus 2, right? So it is basically n multiplied by dv by dt. Okay, so it is, we get dou vr by dou t is equal to minus vr by 2b square into dv by dt, right? Again dv by dt would be equal to minus b. Why? Because since the rate at which the height of the liquid film the rate at which the height of the fluid decreases is equal to the velocity of the plate. That's why dB by dt, rate of change of b, would be actually be equal to the velocity of the plate moving downwards, right? So we would have dV by dt is equal to minus v to give the direction sense of the motion of the plate. So dou VR by dou T would be equal to V square R by 2B square. Okay, so the correct answer would be option number D. Okay, so sorry, option number A, V square R by 2B square. So correct answer is option A. And the next question is, what is the variation of pressure in the radial direction? Okay, so once pressure comes into picture, so now we need to deal with the Euler's equation of motion. Okay, so since we already know the velocity field along the radial direction, so let us okay, I'm sorry. Okay, sorry for the delay. So okay, yes, so as I was mentioning, so variation of pressure in the radial direction that can be found using the Euler's equation of motion. But again, there are certain simplifications that are already mentioned in the question. So if we go back to the question, so sorry for moving to and fro from one page to another, but we need to see the assumptions properly, right? So here in this example, if we consider the density to be constant, okay, so if we consider rho to be constant and then consider the fluid to be inviscid, okay, if we consider the fluid to be inviscid, then we can inviscid and then that we can directly apply the Bernoulli's equation or the unsteady Bernoulli's equation in this problem to find the net pressure distribution, right? So if I go back in this, let me go back to my notes. So we can now implement the unsteady Bernoulli's equation to find the pressure distribution, right? Because some problem can again be simplified by taking certain assumptions. So we can, instead of using the Euler's equation, we can directly use the Bernoulli's equation or the unsteady Bernoulli's equation, right? So once we take the assumption of the fluid to be inviscid and the flow and the density to be constant, we apply the unsteady Bernoulli's equation. Unsteady Bernoulli's equation to get that P1 by rho plus V1 square by 2g plus gz1 is equal to P2 by rho plus V2 square by 2g, sorry, V2 square by 2 plus gz2 is equal to integration from 1 to 2 dou VR by dou T into ds. Okay, your ds denotes the elemental length along this streamline. Okay, now if we take the 2 points on the same horizontal streamline, like if we go to the diagram, so if we take a streamline in a manner that say, if we take say streamline of such manner that say this is the streamline that we are considering, and if we consider 2 points to be here, say 1 and the other point is at 2, okay, at the outer edge, right, 2, then we can essentially ignore the height difference in the Bernoulli's equation. So z1 would be equal to z2, right? So considering the 2 points to be on the same horizontal level, the equation can be further simplified and by just neglecting these terms. Okay, so again, if we consider V2, okay, V2 to be at the outer edge of the fluid, right? So there we would know V2, because since we know V is given by, or let me just write it, VR is given by VR by 2B. Then V at R equal to capital R would be basically V into capital R by 2B, right? So we essentially know V at the outer edge of the fluid, right? Similarly, P at R equal to R would be equal to PA, this is the atmospheric pressure, right? So point 2, let me just write it, point 2 would imply R is equal to capital R. Okay, so once we substitute these values in this equation, we would get that P minus P ATM by rho is equal to V square by 4B square into capital R square minus small r square. Okay, plus the integration from 1 to 2 dou VR by dou T into ds. Okay, so now we need to evaluate this term. Okay, so dou VR by dou T into ds would be essentially be, because we have already evaluated dou VR by dou T, which is equal to V square R by 2B square. And if we consider, since it is along the same streamline, and the streamline is along the same horizontal level, the 2 points are on the same horizontal level along the streamline, so this streamline can now essentially be considered as the length dr. So the elemental length along the streamline can be considered to be equal to dr, or the radial distance between the I'm sorry, it's better to go to the diagram. So what I mean to say is that if this streamline is considered to be this form, and if these 2 points are in such a way that they lie on the same horizontal level, then a streamline, or the elemental streamline length ds can be considered to be equal to dr. Okay, the elemental radial length. Okay, so if we substitute ds equal to dr in this expression, once we do the integration, we will get that this integration 1 to 2 dou VR by dou T into ds would be equal to V square by 8B square into capital R square minus small r square. So once we just club together all the terms, we get that P minus P ATM by rho is equal to V square by 4B square multiplied by capital R square minus r square plus V square by 8B square multiplied by capital R square minus small r square. So this is the net pressure distribution that we need to obtain. So the correct option, if you look here, would be option number B. Okay, so that's the correct option. So now we look into the next question. So it is just 1 second. Okay, sorry for the delay. So as I was mentioning, so the next question is given by this. Okay, sorry for the delay, I apologize. So let's go to the next question. Okay, the velocity components in an inviscid constant density and steady flow field are given as u is equal to a by 2 x plus y plus z, v is equal to a by 2 x plus y plus z, and w is equal to minus a x plus y plus z. Okay, so, and where a is a dimensional constant, consider a line segment in the flow field directed from point P1 to P2, where these are the coordinates for point P1 and P2, and consider the following statements. Line segment P1 P2 is a streamline. Okay, this is the first question, the first statement. Then the given flow field is rotational. and the Bernoulli's equation can be used to find pressure difference between points P1 and P2. Okay, so these are the statements to consider, and these are the following combinations among which are correct. Okay, so we need to check which of the following combinations are correct. Okay, so let us try to look into the each of these statements individually and try to derive the condition so that we can see whether these statements are correct or not. Okay, so let us check the first statement. It is line segment P1 P2 is a streamline. So to do that, let us just find the equation of streamline. From that we will get that dx by u is equal to dy by v. Okay, so if we simplify this expression by substituting a value of u and v, we will get that y is equal to x plus c. Okay, so just take a few moments to see how we derive the equation, then we can go forward. Okay, so again, once you look forward, you will see that both of these terms will get cancelled out. So we will basically get y is equal to some x plus some constant. Okay, then for the line P1 and P2 to be a streamline, both the points P1 and P2 should satisfy the equation of streamline, right? So they should satisfy this equation of streamline. So in order to do that, just substitute the value of the coordinates in this equation to see whether the this coordinates satisfy this equation or not. Okay, so we'll see that for point 1 P1 is equal to 0 0 0, we get the value of constant as equal to 0. Okay, so that's fine. But for point P2 we get that if we substitute the value of minus 3 3 0, we'll get that the constant is c equal to 6, and since the value of this constant is different, thus these 2 points do not lie on the same streamline. Okay, so the first statement, that is the point lie on different point line P1 P2 being a streamline, is not correct because these two points do not lie on the same streamline. Okay, then let us look into the second condition, that is the given flow is irrotational. So in order to do that, just try to find the angular velocity of the flow of the given flow field to see whether it is non-zero or not. Okay, so let us just check the x component of the angular velocity, which is given by half dou w by dou y minus dou v by dou z. Okay, so if we do the calculations, we get that omega x would be equal to minus 3a by 4, and since a is a numerical constant, so and it is non-zero, that's why the angular velocity is non-zero, and thus the vorticity is non-zero, right? Thus the flow is rotational. So so if we look back, so both the statements 1 and 2 are incorrect. Okay, now we look into the final statement, that is the Bernoulli's equation can be used to find the pressure difference between the points P1 and P2. Okay, now comes the interesting part. See, it was told initially while considering the conditions for the validity of the Bernoulli's equation that if the flow field is rotational or if the flow field is irrotational, then the Bernoulli's equation can be applied between any 2 points in the flow field. But there was some other conditions as well which told that if that is satisfied, then also the Bernoulli's equation can be applied between any 2 points in the flow field. And one of those assumptions was that if this product v cross omega dot dl, if this dot product is 0, then also Bernoulli's equation is valid between any 2 points in the flow field. Okay, and how this statement came and how it is valid, I leave it to you as an exercise for you to revisit and go and cross verify whether what I am claiming is correct or not. Okay,
But this is correct, of course, but how it is derived, it is discussed in the lectures. So we can just go back and revisit them, and then try to understand how the solutions, how we have obtained the solution, and how we are claiming this solution to be correct. Okay. So dl would be dx, in this case dl would be dx I cap plus dy j cap plus dz k cap, and for a line segment directed from p1 to p2, dl will be given by 3 I cap plus 3 j cap, because z is 0 in both the z coordinate is 0 in both the cases, so it will be 0. Okay, or essentially it is plus 0 k cap. Okay, that doesn't matter. Then v cross, we need to find v cross omega. So omega x we already found, which is equal to minus 3a by 4. Okay, then omega y we find again. So omega y is given by again 3a by 4, and omega z is 0. Okay, to find v cross omega, we again evaluate this cross product to get that v cross omega is equal to this. Okay, this expression. Now we find the dot product of v cross omega and dl. Okay, we find the dot product of v cross omega and dl to get that this dot product is essentially equal to 0. Okay, and thus Bernoulli's equation can be applied to find the pressure difference between any 2 points in the flow field. Okay, so again this question is very interesting and quite counterintuitive to what we have discussed so far. We told that if the flow field is irrotational, then we can apply Bernoulli's equation between any 2 points in the flow field. But we didn't mention that it is the only condition required, or we didn't mention that if the flow field is rotational, then we can never apply the Bernoulli's equation between any 2 points in the flow field. So this condition of v cross omega dot dl being equal to 0 is also one of the conditions where we can apply Bernoulli's equation to find the pressure difference between any 2 points in the flow field, even if the flow field is rotational. Okay, so it's very important and crucial. So I insist that you revisit the lectures and cross verify what I am claiming here. Okay, so the only correct option is option C. Okay, this only 3 is true. Which among the following statements, then we have the question, which among the following statement is not correct about Euler's equation? So first is, Euler's equation is derived by applying Newton's second law of motion to the fluid flow. That's correct. Euler's equation is valid for both steady and unsteady flows. That's also correct. Euler's equation is only valid if the flow is irrotational. That's incorrect, because there is no preconditions required for the derivation of Euler's equation, and the only condition is that the flow must be inviscid. So it does not mention anything about irrotationality. So the Euler's equation is even valid for irrotational flows, even valid for rotational flows. Okay, and finally, Euler's equation is valid for both compressible and incompressible flow. Of course, there is no strict mention about whether the flow has to be incompressible or not. So the Euler's equation is valid for both compressible and incompressible flows. So the correct answer to this question would be option number C. Okay, and finally, we have the final question is, the stream function of a flow field is given by psi is equal to ax cube minus bxy square. Okay, where a is equal to 1 meter, 1 per meter second, and b is equal to 3 per meter second. Okay, and the coordinates are measured in meters. Find the pressure gradients at xy is equal to 1, 1. Okay, so it's very simple. We can use we need to find dou p by dou x. So it will be equal to, if body force are considered to be is 0, then it will basically be equal to minus rho dou u by rho u dou u by dou x plus v dou u by dou y. Okay, then again dou p by dou y would be equal to minus rho u dou v by dou x plus v dou v by dou y. Okay, so let me leave these calculations for you as an exercise for it to be very interesting. So what you need to do is, let me solve it here itself. Okay, so here u can be found out by this, right? T psi by dou y. So it will basically be minus 2bx y. Okay, and v would be equal to minus dou psi by dou x. So let us keep the minus sign here. And then dou psi by dou x would be 3a x square minus by square. Okay, so these are the velocity components, and just now we need to substitute the value of u and v in these expressions to find dou p by dou y at point 1, 1. Okay, and the important thing is, so once you do that, and here it is given that b a equal to 1 and b equal to 3. So once you do that, you will find that a very interesting result, that none of the options is correct. Okay, there is some printing mistake or maybe some error in derivation, so none of the options is correct. So once you do that, let us go to the calculations. So dou p by dou x would equal to minus rho u dou e by dou x plus v dou e by dou y. So we substitute u is equal to minus 2bxy and dou e by dou x is equal to minus 2by. Okay, plus v is equal to minus 3x square plus by square into minus 2bx, because dou e by dou y is equal to minus 2bx. So if you substitute the value of x and y as 1 and 1 and a and b equal to 1 and 3 respectively, you will get that dou p by dou x is actually equal to minus 36 rho. Similarly, for the pressure gradient along the y direction, dou p by dou y is equal to minus rho u dou v by dou x plus v dou v by dou y. So if you simplify the expressions and substitute the value of a, b, and x and y, you will find that dou p by dou y is equal to minus 36 rho. So after calculation, it was found that none of the options is correct, and actually it should be actually 36 rho. Then the answer would be option C. Okay, so I have done my part. So the problem set was a bit wrong. So I have done my part to cross verify the calculations, but you can also do the same thing and cross verify this particular problem. So let me give it as triple star. It's quite interesting. So you can cross verify it. Okay, cross verify the calculations. If I am wrong, it may also happen that I might have done some calculation mistake, but the algorithm or the gist of the problem is to first find the velocity components from the stream function. So from the stream function, and then substitute it in this Euler's equation of motion to find the pressure gradients. Okay, so that's all that I want to discuss today. So I hope it was clear, and if you have any doubt, again please go back to the lecture by Professor Chakraborty, and I have given the exercise for you to cross verify whether this condition makes the Bernoulli's equation valid between any 2 points in the flow field, even if the flow is rotational. Okay, so that you need to cross verify, but it would be very good exercise for you. Okay, and moreover, there are various points that I asked you to revisit to the lectures and solve it, and then view your solutions parallelly, so that you can cross verify and rectify the concepts. But still, that would be very good exercise for you. Okay, so you can do that, and I feel that's all from my side for this week, and let's meet in the next week. Okay, so thank you and have a good night. Thank you.